Hello, my name is Shahriari, and this is a lecture in a series of lectures on elementary linear algebra based on my book, Retrolinear. The subject of this lecture is one thing: how many solutions does a system of linear algebraic equations have? And we will show that there is 0, 1, or infinite number of solutions. Given a system of linear equations, for example, like the one I have here, x minus 3y plus 5z equals 7, and 4x plus 5y minus 8z equals 2. This is a system of equations. There are three unknowns and two equations, and usually we like to solve them. Instead of solving them, my question is that how many solutions could it have? So theoretically, before we get started, is there any limit to how many solutions does such a system have? If the number of unknowns is 2, if you just have x and y, regardless how many equations you have, you can reason geometric, and we shall see that. If the number of unknowns is higher, then the geometric arguments are going to be harder, and an algebraic argument works much better and it's much more convincing, and that's what we want to do here. What we will do is we will translate the problem into one of matrices, about matrix equations, and use properties of matrix multiplication to answer this question. And this will actually showcase why it's so efficient to think of systems of linear equations as matrix equations. What we will show is that every system of linear equations will have either 0, 1, or infinite number of solutions. But it means that you can never write down a system of linear algebraic equations with 47 solutions, or for 3 solutions, or with 2 solutions. You will either have no solutions, one solution, a unique solution, or if you have more than that, it will be infinite. Okay, so let's think about a case of 2 dimensions. If the number of unknowns is 2, then a linear equation is going to be of the form ax plus by equals c. X and y are the unknowns. A and b and c are parameters. What is ax plus by equals c? Well, that's an equation of a line, of a straight line in the plane. And what does it mean to have a system of equations? It means that you have a number of these lines. To solve a system of equations simultaneously is the same as finding what points are in both lines. So the first line, ax plus by equals c, that determines what points are on the line. The x and y that satisfy that are exactly the coordinates of the point on that line. If you have more than 2 lines and you want to solve a system, then that means you want to solve them simultaneously. You want to find a solution that works for all the equations. So that means that you want to find the point of intersection. So in this case, for example, this point will be the unique solution if you have 2 equations. You can have more than 2 equations that have a unique solution like that one. You could have, for example, another line going right through that point of intersection. You could have 25 lines go through that one point and have a unique solution. But it's also possible that even 3 lines will not have a common solution. These 3 lines intersect, but their points of intersection, they don't have a common point of intersection. Every 2 of them, if you just solve 2 of them, you could get a solution. But when you're solving 3 of them, there's no point that's on all 3 lines. And so there will be no solutions. There's other ways for there not to be a solution. For example, the lines could be parallel. Whether or not there's 2 of them or 28 of them, if they're all parallel, there's no point of intersection. Finally, the other thing could be that you have the lines lying right on top of each other, meaning that you have the same line. You might disguise that by, for example, writing x plus y equals 2 be one of your lines, and the other one be 2x plus 2y equals 4, which is actually the same line, but might look slightly different on the face of it. But anyway, when the lines are on top of each other, what are the points that are common to them? Or even if you have just one line, then there will be an infinite number of them. And so the number of solutions is either 0, 1, or infinite based on the way the lines intersect. There's no way that you can have 2 lines or 3 lines or 4 lines, straight lines, intersect commonly, have all their intersections, all of them intersect in 2 points or 3 points. But you might not be completely happy with that argument, but the algebraic argument will work for this case as well. But what if you have 47 equations and 31 unknowns? Well, we can't, with 31 unknowns, we want to be in a 31-dimensional space. That's going to be much harder to think geometrically about. So, for example, here's a particular system of equations. And what we are going to do is we translate that to a matrix equation. We have done this in a previous lecture, the lecture on matrix multiplication. We went through this in some detail, but I'm going to repeat that quickly. So if you have a system like that, then you write 3 matrices. You write the coefficient matrix A, which has all the coefficients on the left-hand side. Each one of the columns is associated with one of the variables and each one of the rows is associated with one of the equations. And then you have a column vector of the unknowns, in this case, x, y, z, and w, and a column vector for the right-hand side entries. So in this case, 3, 5, and 7. Now, if you look at the matrix equation AX equals B, what does AX equals B mean? It means you take the matrix A and multiply it by the column vector X. When you do that, you're finding the dot product of the rows with that column vector, and you will actually get the left-hand side of the equations. You get 3x minus 2y plus 5z minus 8w for the first entry, and the other ones for the other entries. And putting that equal to B means that you want 3x minus 2y plus 5z minus 8w to be 3. So you're looking for an x for that to work, and that's the same as finding solutions for that first equation. And because you need the two matrices AX and B to be the same, you want all their entries to be the same. So that means you're trying to find X, Y, Z, and W that satisfy all three equations. In other words, that system is the same as the matrix equation AX equals B. So the matrix equation AX equals B, when you see that, whenever you see AX equals B, you're really talking about a system of linear equations. If instead of A, you put the numbers, and instead of B, you put the numbers, and instead of X, you put the unknowns and multiply it out, then you have a system of linear equations. The coefficient matrix is A, the vector of unknowns is X, and the right-hand side vector is B. Vice versa, every system of linear equations, just as I showed in the previous slide, can be translated by a matrix equation of the form AX equals B. Again, if you have a system of linear equations, you make A to be the coefficient matrix, X the vector of unknowns, and B the right-hand side vector, and you will have a matrix equation. So it pays to, whenever you look at a system of linear equations, instead of getting lost in all those variables and coefficients and so on, to think that I'm just thinking about AX equals B. It just seems it's just much more compact and user-friendly. And note that if the matrix A is M by N, M rows and N columns, then that means that you're talking about M equations and N unknowns. Now, the matrix itself is not M equations and unknowns. AX equals B is M equations and N unknowns. Okay, so what are we trying to prove? And we're almost at the end of this short lecture, is this proposition that every system of linear equations over the real numbers, meaning that we're looking for solutions that are real numbers and the coefficients are real numbers, has either one solution, no solutions, or an infinite number of solutions. And again, the content is to say that there can never be 3 solutions or 47 solutions. And in this particular case, it's actually important that we're over the real numbers. It doesn't have to be the real numbers, it could be the complex numbers, but it definitely has to be an infinite field. If you're talking about a finite field, and the proof will tell you why, there might be actually a finite number of solutions other than 0 and 1. Okay, so now we want to prove this. So how are we going to prove that we had every system of linear equations has 0, 1, or infinite solutions? First of all, we don't write down a system of linear equations. What do we write? We write AX equals B. So we say that we have a system, AX equals B. So instead, from now on, whenever I want to think about a system of linear equations, I say AX equals B. A is the coefficient matrix, B is the right-hand side matrix vector, and X is the vector of unknowns. And then how am I going to prove that it has either 0 or 1 or infinite solutions? Well, I will say that assume that it has at least 2 solutions. If it has 0 solutions, you're good. If it has 1 solutions, you're good. But if it has 2 distinct solutions, 2 different solutions, you want to show that in that case, it must have infinite number of solutions. So assume that it has at least 2 distinct different solutions. And then we want to show that from that case, we can get an infinite number of solutions. And then that means that either it doesn't have at least 2 distinct solutions. Well, what does that mean? It either has 0 or 1. But if it has 2, then it has infinite. 2 results in infinite. Okay, so let's say that X equals C1 and X equals C2 are solutions to the system. Now, C1 and C2 are not real numbers, they're column vectors. Because remember, X is a column vector of unknowns, and it depends on how many unknowns you have. So for example, if the matrix is N by M, and M is the number of columns, X is M by 1, and there's M unknowns, and so C1 and C2 are also column vectors with M things in them. Now, what does it mean to say that's a solution into the system? Well, it means that if instead of Every entry in X, we put the corresponding entry in C1, for example, into the system. The two sides are satisfied. Another way of saying that is that if I plug in X equals C1 into AX equals B, it should get satisfied. So in other words, if you plug in C1 for X, that means A times C1, you will get B. Now, A times C1, C1 is a bunch of numbers, A is a matrix, and B is a bunch of numbers. So when you multiply A by C1, you'll get something. But to say that X equals C1 is a solution to AX equals B means that A times C1 equals B. And likewise, A times C2 equals B. So that because C2 is also a solution. All right, what are we going to do? Well, what we're going to do is we're going to look at their difference, the difference between C1 and C2. That's a new vector. And because C1 and C2 are two different solutions, C0 is not the zero vector. I mean, the thing I'm going to immediately say works even if C0 is the zero vector, but later on, the stuff I will say will depend on C0 not being the zero vector. Okay, so what about this guy? Well, let's plug this guy into our system and see what happens. So I'm going to look at A times C0. If I got B, I would know this is also a solution, but I'm not going to get B. So let's see what we get. So A times C0, what am I going to do? Well, C0, what is that? It's C1 minus C2. So I have A times C1 minus C2. Now, one of the properties of matrix multiplication is that you can use the distributive law. So if you have A times C1 minus C2, you can distribute that and get AC1 minus AC2. But AC1, we knew what it was. Because C1 was a solution to the system, AC1 was B. That's one of the things we said. AC1 is B. AC2 is also B. And so what we have is B minus B, and that's the zero vector. So what happened? What we got is that C0 is not a solution to AX equals B. That might be a little bit disappointing. But what we found is that actually C0 is a solution to a different system. What system? The system AX equals 0. So C0 is a solution to AX equals 0. If you take C0 and plug it in for X, those variables, you won't get the B, the right-hand side, but you will get all zeros. Well, so what good does that do? Well, now we are going to do the following. For every real number alpha, there's infinite of those, look at the vector, the column vector C1 plus alpha C0. So C0 was this guy that we just got, multiplied by alpha. Well, you know, alpha is your favorite real number, pi, e, 2, square root of 5, 85, minus 47, any one of those. And you take C0 and multiply by that and add it to C1. C1 was one of the solutions that we had to the system before. How many of these are there? Well, there are infinite of them. There's two things needed for that. First of all, C0 is not 0. If C0 was 0, we would always get C1. But because C0 is not 0, whenever we change alpha, we're changing this. And so we're getting infinite number of these because there's infinite number of real numbers that make these guys infinite of them. This is the place where it's not good enough to have over any field. Like, for example, finite fields would not work for this proposition. So there's infinite such elements, but what good are they? Well, the thing is that these are all solutions. And so I found myself infinite number of solutions. How do I know they're solutions? The proof of the pudding is in the eating. Just plug it in. AX equals B. Is this a solution to AX equals B? Well, put it instead of X to see if it is or not. So I'm plugging in C1 plus alpha C naught into X. And so I get A times C1 plus alpha C naught. And again, I can distribute in and I get A times C1 plus A times alpha C0. What's A times C1? Well, that's B. What about A times alpha C naught? Well, alpha is a constant. And one of the properties of matrix multiplication is that that constant can go anywhere. You can multiply A and C0 and then multiply by alpha, or multiply alpha first. So A C1 becomes B, but A times alpha C naught becomes alpha times A C naught. What's A times C naught? Well, that's 0. So this is B plus 0, and so it's B. So we found that C1 plus alpha C0 is a solution to AX equals B. And because of that, we have found infinite number of solutions because I can change alpha as much as I want, and I can get as many solutions as possible, and the proof is complete. So the thing that I want you to notice is that we didn't get our hands dirty in the system. There was a lot of mileage to be had by looking at matrices as opposed to looking at individual equations and all these unknowns and so forth. We didn't do that. We just manipulated matrices and used the properties of matrix multiplication to have a clean proof that a system of linear equations either has 0, 1, or infinite number of solutions. This is the end of this lecture. Hopefully I will see you at the next lecture. Keep hydrated. Always.